We've just finished going through problems involving electric fields when we have information about either the producer or the experiencer. But there's only been one charge. There's been either the producer or the experiencer. Now we got two charges. We got a question up on the board right now where we have two charges, both producers, where we want to find the electric field strength somewhere in between those two producers here. So let's read the question and figure out exactly what we want to find here. Two positively charged spheres, A and B, with charges of 1.5 and 2 respectively, are this far apart. What's the electric field midway between? Okay, exactly midway between. What's the field? This question is not unlike the quiz question you had in a lot of ways. The quiz question had 3 charges, and you wanted to find the force on one due to the other 2. It only has 2 charges, but in the end, the 3 charges produced 2 forces on the middle charge. These 2 charges produce 2 fields on that spot right in the middle. So what we got to do is draw what is almost a free body diagram. It doesn't show the forces, it just shows the fields at point P. A couple of people this morning had some trouble with this. We have a positive charge here, charge A. There is a field surrounding charge A, and it goes away from it. We don't care about this one, or this one, because we're trying to find the field at point P caused by A and B as well. Let's label this one right here, field caused by A, EA. Now, charge B experiences, or produces, I should say, a field also pointing away from it. We know that it goes away from it because if we put a positive point source or a positive charge in that field, it would be repelled by it. So the field points away from the positive producer. We're going to call that EB. Then we're going to erase these fields right here because we don't really care about it. Right? We care about the field immediately to the right of charge A and immediately to the left of charge B. Now they're both producers, so let's get both of those 4 fields. KQ over R squared. What distance do we use there, eh? What to do, what to do, what to do. What distance do we use there, Lucas? Yeah, since we're looking for the field strength midway between, we divide that distance in half. 3.3 divided by 2 is 1.65. So it's going to be 1.65 times 10 to the minus 2. Okay, let's square that. This side of the room, okay, Fraser's side of the room and over, calculate that one, please. EB, done pretty much the same way, 8.99 times 10 to the 9 times, this time the charge is 2 times 10 to the minus 6, divided by the distance of 1.65 times 10 to the minus 2. This side of the room, Jordan and over, are going to calculate this one, please. Fraser side, you guys got the blue one? Lucas, you got it there? Lucas B? Yep. 10 to the 8? 7? Listen, guys, if you have trouble, a little bit of trouble with the scientific notation, sometimes we're dealing with really, really big numbers or really, really small numbers, and you start counting decimal places going over there, right? And we're worried like, like it's 14 decimal places I got to count over. Am I going to make a mistake on that? Let me show you a little trick here. Let's say we multiplied some numbers together. 5 point times 2.36 times 10 to the 12. Bad example. 5 point. Let's times that by. All right, so we get that number. We want to convert that to scientific notation. We can count the decimal places, right? We can do that. but sometimes it gets a little bit cumbersome when we're counting the decimal places. Watch this. Okay, you don't have to do this, but it's a little trick that will work for you every single time, and it'll save you from counting there. Both ways. If it's 0 point something, 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 or a big number like this. Okay? Hit mode, go down into scientific notation instead of normal. Click enter. Exit that. Now don't hit enter again, because then it'll do the multiplication again. Just multiply that by 1. Multiply the number you just got by 1. So you should end up with the same number, except this time it's going to be in scientific notation there, right? So if it ever becomes cumbersome to do that, because I know that you're working on that there, just do that. It always works. So is that 4.95 times 10 to the 7, you said? Good, thank you. Okay, green side of the room, Jordan's side here. What'd you guys get for this one? Cassie, you got it there? Okay, 6.60 times 10 to the 7 newtons per coulomb. Good. All right. Now, what do we do with both of those values that we just got? Subtract them? Yeah. We're adding, but we're adding a negative number, right? So it's the same thing as subtracting. So I don't really care which way you think of it, as long as you recognize that if they're both in the same direction, we add. Opposite direction, we effectively subtract. So it becomes 4.95 times 10 to the 7 plus negative 6.6 times 10 to the 7. And that's going to give us what? Negative something? What is that? 4.953? No, I don't think so yet. 1.65? Is it negative, Jordan? I think it's negative there. 1.65, did you say? Times 10 to the 7 newtons per coulomb. Listen, if this is a multiple choice question, I guarantee you that obviously that option is going to be there. But I also guarantee you that if you add these both together, make them both positive, that option is going to be there as well. So be very, very careful of that. Okay, those mistakes that are really common that a lot of us can make and probably will make at some point, they're going to account for those. All right, let's try these two questions here. We'll give you about 7 minutes or so to work on these two questions. At least get the first one done so we can take a peek at it if we struggle with it. Then we'll move on, okay? All right, let's take a look at number 1 here. It says, calculate the net electric field at a point 2.10 times 10 to the negative 2 meters to the left of the, basically to the left of charge A there. That's going to be a point over here somewhere. 2.10 times 10 to the negative 2 meters. All right. Both of these charges cause electric fields. And both of these charges, being positive, cause electric fields that point away from the producers. So the first one is going to produce an electric field that looks like this. We don't really care about this part of it and this part of it and this part of it. All we care about is the electric field to the left of charge A. Let's call that EA. Right, the field caused by A goes away from the positive producer. If it was a negative producer, then the field would have pointed towards it, but it isn't. All right, second charge also produces an electric field that looks like this. The field to the left of B, even way to the left of B, points to the left. Again, away from the positive producer, charge B. Let's get rid of these, because all we care about really is the field way over here as a result of charge B. Both of these are in the same direction. That means when we get the numbers, we're going to simply add them up. Usually we make them negatives because they're to the left, but it doesn't really matter. Okay, let's get EA. KQA over R squared. 8.99 times 10 to the 9 times QA is 1.5 times 10 to the negative 6. Divided by the distance, which is 2.10 times 10 to the negative 2. And then we got to square that. Okay, this side of the room, Fraser's side of the room, you guys are going to get that number for me, okay? The second one, EB, this one's a little bit trickier. It's 8.99 times 10 to the 9 times the charge B, which is 2 times 10 to the minus 6, divided by what? What's the value of r squared there? What number do I put in there? Good. Good, Oliver. We're going to put the total of those because when we're finding the field strength caused by B, it's as if A isn't even there. Just because they're separated into two separate distances doesn't mean that we're going to keep them separated, right? We need the distance from B to that point, which mathematically is simple. Just add them up, right? So 2.1 plus 3.3 gives me 5.4 times 10 to the minus 2. And don't forget to square that. You guys on this side of the room, Jordan's side of the room, are going to get me the green one here. Blue one, who's got it? Terry, you got it there? Yeah, it doesn't matter. Whatever's convenient. 10 to the 7. Okay, newtons per coulomb. Good. The green side here, Jordan's side of the room. Anybody got that one? Already have that one already? Ten to the 6. Okay, thank you. All right, good. Add them up. It's going to give me, I assume, 3.67 times 10 to the 7, or negative 3.67 times 10 to the 7 when we add those up. How many people didn't want to include charge B there? How many people were, as they were doing this for the first time, before I explained a couple things, just ignored charge B? That's a common mistake, right? That's why we do these questions, is to learn from those mistakes when it doesn't really matter, so we don't make it when it counts. How many people forgot to add these two distances together? 2.1 plus 3.3. Point that Oliver just made. No, everybody got that? Good. That would be a common mistake too, relatively speaking. All right. What I want to do right now is assign a few questions on page 553 for homework. And then we'll do a couple multiple choice questions for the rest of class here. So we're going to do these questions for homework tonight, questions 1 and 3 to 9 on page 553. Now I want to go through a few multiple choice questions. I'm going to have you submit all of these, each of them as multiple choice number 1. So we'll do one at a time. Firstly, number 44. Go to the link, submit it as multiple choice number 1 when you've got it finished, please. All right, guys, take a look at the results here. We got 96% of you said A, 4% of you said D. Let's hope the answer is A. Okay. The types of charge present on X and Y are what? Well, first of all, without even looking at which way the field points, we know that these charges both have to be like charges, either both positive or both negative. We know that because of the shape of the field. If they were opposite charges, then the field lines would join up with each other. Okay, whichever way they went, the field lines would join up with each other. So X and Y have to both be either positive or both be negative. Well, let's hope they're negative. They are, in fact, negative. But how do we know that? Okay, we know they're both the same charge by the shape. We know they're both negative by the direction of the field line here. The field line points towards the producer. So since we define the direction of the field as the way a positive would move if placed in the field, it's got to be a negative particle, a negative producer. All right, let's take a look at the next question, 46. We're going to submit this one as multiple choice number 1 as well. All right, taking a look at number 1 here, guys, or 46. We got 74% of us are saying B. And we got a significant number of us that are saying A as well, and some that says C and some that says B. So we got all options here. Listen, most of the information that they give us here isn't really relevant. Most of it isn't relevant. We care only about the direction of the electric field caused by 1 and 2. Now, in the end, number 1 causes a field that points towards it. Right? The field always points toward a negative producer. The field always points away from a positive producer. So if we get a field pointing to the left as a result of number 1, and a field pointing to the left as a result of number 2, then the net field has got to be to the left. So the answer is going to be B. All right. Let's try this one. This one gave people trouble this morning. So pay really close attention to this one. Watch for little things. This was not a well-done question this morning, even though it looks like it should be a relatively straightforward one. See what you can do with that over the next, let's say, 2 minutes here, and then we'll take a look at it then. Okay, let's take a peek at this one. The intensity and direction of the electric field produced by an alpha particle at a distance of 5.0 times 10 to the minus 11 is what? Here's the alpha particle. The alpha particle is a charge of 3.2 times 10 to the minus 19. That's on our data sheet, right? It says 2 times the elementary charge. The field produced by the alpha particle this far from the alpha particle. I want to find the field strength right there. Clearly, the alpha particle is a producer, so let's use the producer equation. KQ over R squared. Uh, 3.2 times 10 to the minus 19. A lot of people this morning made the mistake of using 1.6 times 10 to the minus 19 as the charge, as opposed to 3.2. Okay, that would be a common mistake, especially at this point in the year when you're not that familiar with what an alpha particle is, right, Aisha? The distance here, don't forget to square that. That's another mistake that people make. Do the math there. I think it works out to be 1.2 times 10 to the 12. And we know it's going to be away from the alpha particle because the field always points away from a positive producer. We good there? All right, that's it for today, guys. Don't forget your homework tonight. That check and reflect page. Let's get those done. We'll take a peek at them tomorrow. And let's have ourselves another little quiz tomorrow on electric fields, the whole electric field stuff, okay?